This video is going to look at topic 3.9, which is the separation of solutions and mixtures. The objective for this topic is to explain the relationship between the solubility of ionic and molecular compounds in aqueous and non-aqueous solvents and the intermolecular interactions between the particles. So first, let's talk about how you separate solids in solution. So if the solids are not dissolved, it's pretty easy. You're going to use filtration. So anytime you have a reaction that results in a precipitate, or if you have undissolved solid and you want to separate out that solid from the solution, you're going to use some sort of filter. So there are lots of different kinds. We don't really need to know specifically for this class, but it typically involves some sort of fine mesh or paper and either a funnel or some sort of container to hold the filter and then whatever the liquid's going to go into. So oftentimes in this class, we'll use filter paper and a funnel into either a beaker or an Erlenmeyer flask. If you have a solid that is dissolved in solution, you can evaporate out the solvent and the solid will remain. And so you can do this for either ionic or covalent solids that are dissolved in solution. It doesn't matter as long as it is a solid that dissolves. If you evaporate the solvent, then the solid's going to remain. So a common example of this would be salt water. So if you dissolve table salt in water, and eventually the salt is going to all disappear. It's going to be dissolved into the solution. If you let the water evaporate, you'll get the salt back out at the end. Now, if we have liquids in solution, things get a little bit more complicated because you can't just separate this based on the size of the particles. So when we talk about filtration, that's what it's relying on, is that the solid particles are significantly larger than the liquid particles, which makes sense. So the filter can catch the large particles. Well, if everything's a liquid, then you can't separate just based off of particle size because they're all going to be essentially the same size. So what we're going to use is we are going to use the differences in intermolecular forces to separate based on solubility and boiling point. One of the primary ways that we do this is using distillation. So distillation relies on the boiling point of the different liquids in the solution. So anything that has stronger intermolecular forces are going to have a higher boiling point. So if you have a solution with 3 or 4 different liquids, whichever liquid has the higher, stronger intermolecular forces between those particles is going to have a higher boiling point. It's going to need more energy to make it go from a liquid to a gas or to break those intermolecular attractions. So this means that as you heat something up for distillation, because that's how distillation works, you heat up your mixture and then you condense at different times, at different temperatures to get the different substances off. So the lower boiling points are going to separate out first, and the higher boiling points will separate later. So if you condense off the side of a distillation column, the first thing that's going to condense are the things that have lower boiling points because they didn't require as much energy to evaporate. And then as you continue the distillation, as you continue to heat your mixture, the things that have a higher boiling point are going to evaporate later. So there's 2 different setups for distillation that we can look at. So this is a common one that you'll see in a chemistry lab. So we have over here there's my mouse. You have over here a round bottom flask. In this case, it looks like it's in an oil bath, but either way, it's being heated up. So this is some sort of solution. So as it gets heated, the particles move faster and they're going to turn from a liquid to a gas. So they're going to evaporate. They don't have anywhere to go except up the column. And then once they hit up here, they don't have anywhere else to go. So they're going to keep traveling down this way. So this is where you flow cool water around the outside of this tube. So this is a double layered tube here. So the gas goes through the inside, and as it gets cooled down by the cooling water from the outside, it turns back into a liquid. And then it falls out into the collection, whatever you're collecting it in down here. And what you collect is called the distillate. So the stuff that you're going to collect first has the lower boiling point, and the stuff that you would collect later would have the higher boiling point. So it's important to know what's in your mixture because then you can know, anticipating based on, so you notice up here there's a thermometer. So that's telling you what temperature it's at, which tells you what's coming off of your solution. This is also a method, I'm going to move my, there we go. This is also a method that's used to refine crude oil. So the previous setup was a setup for a chemistry lab, so a very small, relatively small distillation setup. This distillation setup could be literally stories of buildings tall. I worked one summer and saw a distillation column that was literally 3 stories tall in a building. So what happens with crude oil, so this is called fractional distillation. So instead of distilling off one thing at a time, you have this taller column where it's heated at the bottom. So the bottom's going to be the hottest. So the things that come off the side. And so then you have all these little side pieces that come off. So what comes off at the bottom is going to have the higher boiling point. What comes off at the top is going to have the lower boiling point. And so it's cooled as you go up. And so this is called fractional distillation. And so the things that are large, have high boiling points are going to come off first, or they're going to come off down at the bottom. The smaller, low boiling point things are going to come off at the top. There we go. Okay. There's another type of separation that we can use, especially for solutions, that's called chromatography. And there's actually 3 different types of chromatography. There's paper, thin layer, often called TLC, and column chromatography. Chromatography relies on 2 phases, a mobile phase and a stationary phase. And your phase, the mobile phase is going to be either a liquid or a gas. So that's the piece that's going to move your mixture through either the paper, the thin layer, or the column. And then your stationary phase is going to be either a liquid or a solid. Now, the idea here is that your mobile phase is going to basically dissolve or carry the things that have similar intermolecular forces. So we use a phrase oftentimes when we talk about solubility where like dissolves like. And so we want things with like intermolecular forces to move with the mobile phase, and we want them to be different or opposite than the stationary phase. So you want pieces of your mixture to basically move with your mobile phase and then the other pieces not move with the stationary phase. So your choice of stationary versus mobile is going to depend on your particular mixture. And also whether you're using liquid or gas or solid is also going to depend on the mixture and the components. So the less interaction that you have, the more things are going to move. The more interaction you have, the less things are going to move. So these are some diagrams of what the setup looks like for our different types of chromatography. So with paper chromatography, we have a piece of paper and you mark the start line, and your solid phase is the paper. Your mobile phase is whatever solvent you're using. And so what you're going to do is you're going to watch the solvent move up the paper, and it will carry with it different components of your different mixtures. So each mixture would be represented by one of the dots down at the bottom. So what you'd see here, X would be your unknown. So X is a combination of A, B, C, D, or parts of that. And then A, B, C, D are your different components. And so we can match how they move to what's in the mixture to be able to tell us how much is in that particular mixture. So notice here, we're just taking a sample of our mixture. We're not actually testing the whole mixture. We're just taking a sample of it and we leave the rest of the mixture alone. TLC or thin layer chromatography is extremely similar to paper chromatography. Just in this case, instead of using chromatography paper, we use what's called a TLC plate, which usually has some sort of plastic type backing. And then some sort of silica or similar coating on the one side. But the way it works is the same as the chromatography paper. So your solvent is your mobile phase down at the bottom, you draw a starting line, and then you look at how things move up the paper. The last one is column chromatography. So you use what kind of looks like a burette, and you have a stationary phase that fills your burette. It's usually some sort of jelly type substance, but it's a solid, and that makes your chromatography column. And then you'll put your mixture up at the top in a layer, and then you'll use your mobile phase, and you'll watch how your mobile phase carries down the different components. So then you can watch the different components separate out, and you can actually collect the different pieces. So paper and TLC are a testing method, not a separation method, whereas column chromatography could be a testing method, but it can also be used as a separation method because you can actually put your mixture solution at the top and then watch how it separates and separate out the different components. You can't get back from chromatography paper or from a TLC plate the actual piece that you tested. So that part's done. So those are used more for testing, and column chromatography is used more for actual separation. So that gives you a little bit of an overview of our different separation techniques and why we might choose different techniques at different times.